Okay, I think we can get started. Um, I didn't quite manage to get to inviting people to GitHub yesterday. I'll try to do that this evening. And that means homework one will go up probably tomorrow. Um, so what that will look like is it'll just be repository with your username and homework one on it under the course organization. I think the way that I've structured it is that there will be a README, which is general like guidance for like how to do the homework. Nothing super exciting there. And then a QMD file that actually has the question and then a section for wherever to put stuff in. So if there's a write-up, write it up. If there's a derivation, LaTeX it or include an image. If there's code, include the code there. And though again, for all the assignments, there'll be a combination of sort of the three things there. Yeah.
What lecture does homework
Probably through today. There may be one question that goes on to like the beginning of next week, but it'll sort of be like the last question will be the one that's there. And there'll be very clear guidance in terms of there, because again, like there'll be at a minimum one question that is just for the people enrolled in 644. That will be clearly indicated. So again, if you're enrolled in 644, you need to do it. If you're in 344, then it becomes an optional extra credit thing. So that'll be there. It should be clearly marked. But if you have any questions, let me know. And then the first lab will be on Monday over in Physics 130, wherever that is. I've never been to the building, so I can't help you. But TAs will be there to help. There's not sort of other things planned. So look at the homework ahead of time. Come with questions. I'll ask them to like prepare maybe one or two sort of sample problems that's related to the homework or the lectures. But again, the most useful thing will be to come in with questions about the actual homework. So prepare accordingly. Okay. So today what I want to do is sort of wrap up and put some closing thoughts on where we were last time, was again sort of about predictions for models, particularly around thinking about predictions around the expected value versus the observations. And then we'll talk a little bit about sort of residual analysis as an approach, and then sort of make the transition into generalized linear models and just talk about some baseline stuff there that we need to be on the same page with, because just make sure that everybody's got the same background. So some review, and then just looking at, again, the basic fitting the models, some basic diagnostics, and then what the Bayesian model looks like there. Okay, so just to point out, there is this Duke STM package. It's living on the course organization. It's basically just helper functions that will sort of fix things that are wrong in packages or add some extra stuff along the way. It's fairly well fleshed out already. I will constantly be adding things to it, so you may need to update it as we go. But you can just install it from GitHub with DevTools install GitHub. I'll try to call it out in the slides and elsewhere when I'm using it. So far, like the only thing we saw was like the calculate CRPS function from last time lives there. I've tried to add, not good, but at least minimal documentation for the function. So again, it's in there. So if you do question mark calc STM, calc CRPS, it should give you some indication of what's going on there, at least what the parameters are, arguments. If something is confusing or not working there, ping me, open an issue, send an email. I'm happy to fix it, but we'll try to keep that updated as we go. So by way of that, just to show you a quick example, another helpful function that's there is I mentioned last time that the default ePreds draw or prediction underscore draws from TidyBayes is slightly broken insofar as it does not carry the chain or the iteration information through, which is a little bit obnoxious. And so there's a ePred draws fix and an ePred or predictions draw fix and a predicted draws fix and residual draws fixed that are implemented there. And it just takes care of like filling in that information so that that's there, so you can group by chain, group by iteration, that kind of stuff if you are so inclined. So that's there. It's implemented as part of the package. So we'll be using it today. I just wanted to make sure that we're on the same page as like where that's coming from, what it's doing. Feel free to look at the code there in terms of what's happening, but it's basically just doing a join to bring that information back in. So I was not successful getting them to fix it between last year and this year in the package. At some point, I will put a pull request in or something, but I didn't get to that point. So it's not 100%. It doesn't implement all of those functions, but again, the ones we're going to see in class for your homework and otherwise, it's useful. It's there. So you can take advantage of that. Okay, so where we left off was this sort of conclusion where we had tried to calculate these empirical coverage probabilities from our posterior draws, and we saw that they were massively undercovering. They're much too narrow. The only difference here from what we did last time is we were doing the calculations by hand to do the predictions. And so what I want to highlight is what we were doing by hand was effectively calculating y hats. And when we do that, that's constructing what's traditionally called the confidence interval as opposed to the prediction interval. And that's much too narrow, which we then should not be surprised that the coverage probabilities don't make sense because I'm trying to compare apples to oranges in that particular case. So this is just exactly the same code with minus the previous steps where I'm now just doing it with that ePred draws fix. Yeah.
So the confidence interval is on mu?
Y hat, mu, yeah, whatever you want to call it.
And then the prediction
Interval is y.
Y.
Yeah. So again, that's it, coming from like stat 210, what we call them in those particular cases. They're both confidence intervals. It's just making a distinction about one is about sort of the prediction around the line, the other one's about prediction around the data, the observations. And so if you actually look at a plot, it makes sense why the coverage probabilities are terrible, because those are the intervals that I was just using. So they're much too narrow. It's just about the line. It's not saying something else. And again, it makes sense because I'm essentially ignoring the residuals there. It's much too narrow to cover. Yeah.
Are you making these on the posterior draws?
Yeah.
That's what D is?
Yep.
Okay.
So this stat interval is basically just for each of those draws, draw the 95, 80, and 50% credible interval.
So they're credible regions, right?
Yeah.
Not
Mhm.
confidence.
Yeah, so they are credible regions, and they have, hopefully, proper coverage for y hat, not y. So again, the whole point is just to make sure that we're comparing the right things when we look at this stuff. So when I'm trying to see whether y is in the interval, I need a credible interval for y. Checking whether y hat's in the interval is not interesting because y hat is not observed. I've estimated it, so my interval should all cover those. It's where the center of them is. So again, it's just making sure that you're comparing the right things as you go through here. And generally speaking, in the Bayesian context, most of the time, ePred is going to be the wrong choice. We want to talk about the interval of the whole thing, the observations, the data. That's what we're comparing it back to. So again, just something to be careful of. And it will get further complicated when we get into the GLM case, because then again, we have different things to talk about, whether we're on the linear scale, the transform scale, or the predictor scale. So we'll go through all of that as well, but that's sort of why we're doing all of this. The right one, so again, the only difference here is I'm using predicted draws instead of ePred draws. So now this is the full posterior predictive distributions for y. So those look appropriate. Those have the appropriate sort of coverage intervals. So now this makes more sense. So in this particular case, they're not great, but they're not terrible, right? They're at least in the neighborhood of where they should be. So our 50% credible interval is a bit narrower than it should be. Our higher ones are a bit wider than they should be. Not terribly surprising given, again, this is not a good model for these data. There's lots of uncertainty. But there's also the point of why I'm using this particular model in this example is because this makes the example very clear because the relative size of the residuals is large, which is why those numbers look so bad. If the residuals were smaller, they wouldn't look so bad and you might be more easily confused and mixed up. So again, that's why it's really important to have the mental model to figure out what's going on. So again, this is just a way of sort of checking for the calibration of your model. The coverage is going to be determined by your choice of model, like what likelihoods we used, what priors we used, all the rest of that. So if this is not behaving, we need to change the model in some sense. Like that's how we fix it. And again, it's just a way of sort of checking ourselves along the way. RMSE. So again, we calculated the RMSE for the confidence interval, not the prediction interval. In this case, I would not necessarily argue that one is right and one is wrong. They are just different, okay? So in that case, the use of RMSE is going to be about comparing model performance. So we just want to make sure when I'm comparing different models, I'm comparing the same thing that are compatible with one another. Note the values are different, the distributions are different, everything is different other than within a given approach, they are consistent. Again, I would generally say for most of these kinds of things, this side makes a bit more sense as to what we want to look at, sort of capturing everything, but it's not sort of, using it for y hat is not wrong necessarily. And same thing for CRPS, we can do it here. So again, I can calculate it either way. In this particular case, I would say the one on the left is wrong, right? We're trying to like say, what's the interval there? For very narrow interval with our prediction point off here, those things are going to be inflated. They're a lot larger than they should be. This is our actual prediction for y, so that's what we want to compare it to. So that would be the right choice in this particular case.
So CRPS should only be on
Y.
predicted.
Yeah. Again, that's not to say that there might not be a situation where you have an observed value of the y hat or the mean or something. There can be more complicated situations, but for basic regression kind of things, yeah, we want to predict the observed value and then compare that to the distribution that we got for that posterior predicted distribution. Okay, so there's actually a great blog post by Andrew Heiss talking about all of this, and it came from a place of he was using BRMS and Stan in his class, and he found all of these different like draw functions and stuff super confusing and really annoying, like which should I use when? His students got confused. So like this is him like sitting down and writing 3,000 words to sort out his own thoughts, which I find very impressive. But he does a really nice treatment of going through all of it, and then he also went through and like created these beautiful like Illustrator diagrams of like what is meant by each of these things, what's going on with it. So in this case, like the posterior ear pred is basically the expected value of y, which is y hat, which is mu, same thing. Yeah.
And so the reason posterior predict actually goes to y is because we're allowing for that extra noise.
Exactly. So it's basically drawing from this normal. That's the prediction that we're getting out.
And how is it defining mu in that normal?
That's just the x beta, y hat, whatever
So
it is.
it's not doing an e-pred draw to get that mu, and then
No, because again, that mu is fixed because we have those samples from the posterior draws already.
okay.
Because same thing with sigma. Sigma is for iteration I chain C. We have a particular value for that.
So for each iteration I chain C, we have a mu and a
Sigma, and I just
then
draw
we
from
make
that.
one draw from that,
Mhm.
and that's our
That's-
posterior predict y.
Exactly, yeah. So he goes through all of this. The other part of it is he also does this for GLMs. We will loop back and touch on that again and talk about it in that particular context, because again, there's a couple other edge cases we need to worry about there. But it does a nice job, so again, I just linked it there to see, but I particularly like his diagrams to sort of explain explicitly what's going on, what each of these things is coming up with. There's also, we're not going to use it, this linpred, which is basically just another way of drawing y here. That is different in the GLM case, which is why it's being presented here, but not something we need to worry about right now. Okay, so this is going to be just sort of a very quick hand-wavy kind of thing, but it's going to justify a lot of what we're going to do later on in terms of thinking about how to build a model for a complicated data source. Again, it's not going to be necessarily this exact approach, but this is like a naive, quick kind of thing of let's look at a simple discrete time series model that has some periodicity and has some other complications. How might I go about trying to fit a model to this in practice? So we'll come back and look at this a number of times because it's a good example. This is this sort of historic data of tracking carbon dioxide levels from the observatory on Mauna Loa. And so it's something that there's an even longer range of this, but from like the 70s that they've been tracking it, and it's going up. But there's also clearly periodicity to it, so it's seasonal. It goes up and down in the summer and the winter, and that oscillates. So we want to come up with a model that sort of predicts where CO2 is going to be several steps forward in time, like a month out, a year out, 10 years out, that kind of thing. So there's a lot going on. There's a lot of things to capture. And the general argument that I'm trying to make here for an approach to use is don't try to do everything all at once. Don't try to use a catch-all model that does everything really complicated. Do things iteratively, build up the pieces. And very often the way to do that is to fit a simple model, get the result, look at the residuals, and then whatever's left there, think about fitting a model to the residuals, and then get another new result, look at the residuals again, and sort of iterate through that way. And that's what we're going to try to do here, again, just using LM as a simple way. Again, this is not the right way to do it, but it's a way of getting sort of a good idea fairly quickly of what might be the right way to do it. So I look at the data. I think, oh, it's going up as the year increases. So let's just try it with a linear term for year. So I can include that. Captures the main trend of the data to some extent. And on the top is the current sort of data, my predictions, and then down below is just a plot of the residuals against X. So, okay, it's better than it was. We captured something, but there's clearly still structure in the residuals. And so the name of the game is, as we're doing all of this modeling, everything we're trying to do is get to the point where the only thing left is noise in the residuals, some irreducible error. And once we get to that point, that's when we stop, or at least as close as we can get. There's always the risk of overfitting, risk of other kinds of things. But again, we're going to be constantly playing this game of fit a model, look at the residuals to see how we're doing, fit another model, look at the residuals, see how we're doing. So in this case, I'm going to do the iterative approach, which is not quite right, and we'll talk about why that is in a second, which is to say I'm now going to just fit a model directly to the residuals and see what I come up with. So in this case, what we can clearly see is now that I've basically detrended the data, there's clearly a very strong seasonal pattern, so let's include that. What I can include here is just month of the year as factor variables. So like just January, February, March, April, May. And again, this data is observed once a month throughout the multiple decades. So some periodicity, let's add month as a factor. So again, I'm taking the residuals from the previous model, fitting it out. And that does pretty good. It doesn't like get a nice smooth curve, but it does a pretty good job of capturing the major trend. So again, we know that there's certain months of the year that it's sort of peaking and certain months where it's at the lowest and then everything in between. So what we get now is something that looks better. So again, it's still structured, but it's less structured than it was, which we're going to call a win in this particular case. This is something that now does not have any like obvious pattern, and so the naive, simple tool in that particular case is to say, okay, I've got a squiggly line that I don't have something to fit. I'm going to put a polynomial in there because that'll do a pretty good job. Not a good job for forecasting because polynomials go nuts once you go past the support. Like they do all sorts of crazy things. So not a good option for time series models other than like very low rank polynomials. But what the hell, we'll try something here. So let's put in like polynomial rank 5. Again, you could use this as like a tuning thing, like let me try different ones and see how I go. I'm just picking a number to come up with something. So better. There is still structure here, but there's not a lot of it. It's a lot better than where we started from. So again, this is looking more like noise, but again, you can still see these sort of parts where I'm missing things, where it's sort of like up together and then down together. Again, we will talk about ways of quantifying this and measuring it explicitly, but there's still evidence of like autocorrelation in that plot. So basically, points that are close to each other are more likely to be related than points that are far apart. Yeah.
What does the poly function do?
Basically, it's not quite this simple, but it's in essence putting in x squared, x cubed, x to the 4th power, x to the 5th power as features in the model.
Okay.
So you can do that. It's slightly more complicated because you do it as like orthogonal polynomials. There's a particular form for that so that the columns are independent, but basically that's it.
Okay.
So it just gives us a squiggly line. So in that case, I could say like, good enough. Again, I could go chasing my tail and really go down the rabbit hole and like put a polynomial of the 12th order or something. Those are too wiggly. I'm then just chasing the noise at some point, and it's really hard to distinguish. I'll probably want to come up with something better than that. But again, for a relatively parsimonious, simple model, this is not doing a bad job, particularly given where we started from. So we can put it all together and fit it. One of the issues here that we need to be very careful about is because I was doing this iteratively and I was fitting to each residual as I went, I've actually introduced a model that was rank deficient because I've introduced a linear term twice. And so now when I go back and like just fit the raw data to all of the features, I now have 2 columns that are basically just the date as a linear term. So that's not okay. Those are like perfectly correlated. So that's why this one is coming up as NAs. I could drop date from here and then just have poly 5, but that wasn't exactly the model we fit before because we were doing it iteratively to the residuals. So there is a difference between like one thing after another as we go. But otherwise, it's basically the same. Most of the features are significant. I don't care that they're significant, but that is at least saying like they are doing something useful. The effect is reasonably large. And like all the terms of my polynomial are reasonably large. So again, seems like it's doing a decent job. And this is one of these things where it's like, if you look, it actually does a shockingly good job of fitting the data. And this is one of the things that you can lose the forest for the trees of losing track of what is the scale of the residuals as we go, because they're sort of constantly on the same thing. So this is from like 1 to -1, the previous one about the same, but before that we were like -3 to 3. So like a 3x reduction in the residuals is a pretty big deal. So we are doing a lot better. So yeah, a fairly simple model. We can come up with something, and then the residuals don't look great, but they also don't look terrible, particularly given where we started. So this kind of game of iteratively building a model, of start with the simplest thing and then add features in as we go, is going to be one of the most useful ways to do this kind of thing. So we're going to spend a lot of time looking at residual plots to say, what's wrong with this? How can I go about fixing that as best I am able? So that's just sort of the motivation, the justification to look at this. If we then look at like the RMSE as well, we can see that like as we go with these things, it does help. So just date alone or just month alone doesn't do a very good job. We need also that plus the linear trend. So just doing date and month does a pretty good job. We're now down to 0.593 RMSE, but then adding that with this polynomial is able to sort of sink it further. So again, this is the better model. This is what I might go with. This is not any kind of formal model selection process. We will talk about that a little bit later, of using like selection criteria like AIC for certain models. But again, smaller error is better. That's what I'm going to opt for, as long as I'm not creating like a crazy complicated model. And again, note the difference from here and here is like 12 features or 11 features between the two. And that makes a pretty big difference, pretty big savings. And like from here to here is like from this one to that one is 4 additional features to like cut the error in half. It's not bad. So again, not to say that any of these things is these models are wrong. Some models are useful. The point is just to get into the habit of like thinking about building things up, and again paying attention to the residuals, particularly because we want to look for the structure there, because the structure is informative. We can take advantage of it in some sense, and that's essentially what this class amounts to. Take advantage of the structure and the errors because you can do something useful with it. Okay, so with that said, now we'll talk about GLMs. And the point of why I want to justify residuals is because we want to look at the residuals in the GLM as well, but looking at residuals for GLMs suck. It's hard, they're complicated. So we're going to spend a little bit of time talking about that and how we can at least make it slightly better, and then what that looks like in practice. Okay, generalized linear models is basically just an extension of a linear model to different kinds of outcome variables. So basically the idea here is I have observed data that follows some kind of generative process that is not a continuous numeric value in some sense. So the most common cases are like a binary outcome for classification, so logistic regression, a multinomial outcome, so multiple categories, probabilistic outcomes, so things that are between 0 and 1, or count data. So in that case, I only observe integer values of outcomes. So in those cases, what we want to do is capture that in some sense so that I'm not predicting values that don't make sense. So like if I have a model for the number of cases of tuberculosis, it doesn't make sense to predict 3.5 cases for a particular region. I want a model that takes into account the physical reality or the properties of the data that I'm trying to observe. So the basic way in which we set this up is we choose a probability distribution, generally from the exponential family, that describes our response variable. So if I'm looking at count data, that's going to be a Poisson or something like that. If I have a binary outcome, then it's a Bernoulli distribution. If it's a like multiple observations of a Bernoulli, then it's a binomial. If it's multiple classes, then it's a multinomial kind of distribution. What we then have is the linear component of the model. So that'll just be a typical regression type thing. So of the form x beta, we set that equal to the term eta, just to keep track of things. And then what we're going to do is set up a link function that connects the value or the expected value of our distribution from part 1, so our observation process, to the value of eta. So basically what this is to say is that I have some parameter from the model, which is essentially the expected value of y, which follows whatever distribution I'm interested in. So this is more concrete in the case of like a Poisson. The expected value of y for a Poisson is lambda, the rate parameter. The expected value for a Bernoulli is p, the probability of success parameter. And so what this does is it connects that parameter to the linear term by way of a transformation function. And so the general reason for that is x beta makes predictions between negative infinity and positive infinity. Our link function basically just maps that to whatever the scale of our parameter of interest is. So the probability parameter from a Bernoulli is between 0 and 1. So that's why we'll use a logit link, because it maps from the inverse logit maps from negative infinity to positive infinity to 0 to 1. For a Poisson, we'll use a log because that ensures that the lambda parameter is positive, so on and so forth. So again, it's just a mapping from that linear prediction term to something that makes sense for our parameter of interest for that particular model. So in the case of Poisson regression, my observations are the yi's. They follow a Poisson distribution with a particular rate parameter, lambda sub I, and then the canonical link is the log. So basically, the log of lambda is set to be equal to xi beta, and so the idea then becomes lambda is equal to e to the x beta. So that means it's strictly positive, greater than or equal to 0. So then it's a proper rate parameter for this particular distribution.
So is the link in this case g of x is x?
No, so the link is just here. So it's g of the expected value is equal to eta,
Is equal to,
the x beta term. Yeah.
but g is log.
So g in the Poisson case canonically is log. Yeah. You can pick other ones, but yeah.
This is maybe silly. Why do you condition on x?
Because that's the data.
Why do you care?
Well, because I want the parameter to depend on the data.
Okay.
Basically, I'm trying to determine the parameter given the data. So I need to know that. Because basically, I need to treat x as known when I'm doing this calculation.
Okay. Your sheet is fixed.
Yeah, that's why we're conditioning on it. In the case of like logistic regression, yi is Bernoulli with probability of success p sub I. Then I have logit of p sub I is equal to x beta. And so again, what this allows me to have is a separate parameter for each of the observations, but it's tied to the data in some sense, so that I want to learn that. That's what I'm trying to inform myself on. So again, we've all seen logistic regression in some form, not maybe represented in this way, but it's the same basic idea. So that's why we'll take the time to do the Poisson regression example, because it's probably less commonly seen. But turns out Poisson regression shows up a lot, particularly in spatial modeling, disease modeling, where what you're looking at is incidence of a disease in a particular location. And also similarly, like binomial regression is also another example, because again, the risk that's associated with a disease occurring in a particular location comes up a lot. So those are kinds of common modeling frameworks that you might see there. So old data set, but is at least simple enough to work through quickly and small enough to easily fit. So this is numbers of AIDS cases that were diagnosed in Belgium at the beginning of the epidemic. So in the sort of early 80s through the early 1990s, as the sort of exponential growth in the cases, when it was sort of first discovered at UCLA and then started being diagnosed more widely around the world. So in this case, what we have is count data of the number of patients that were diagnosed with AIDS in the entire country of Belgium for each year from 1981 all the way up to 1993. So what we have is sort of increasing growth, and then it does seem to sort of plateau a little bit at that particular point in the early 90s. So we want to fit a model to this. We want to know something about the rate parameter and how that depends on time in terms of figuring out something about what's going on. So fit it, we're going to use GLM. Cases predicted by years, pulling in from the AIDS data frame we just had. And so here, unlike sort of the standard logistic regression, the default there is binomial. We have to specify the family that we want. So here I'm specifying Poisson because I want a count data model. And again, the default, I can specify the link function there. The default will be log in that case if I don't specify it. So goes through and fits it. We get an intercept and a beta coefficient for year. We also get some other statistics, the null deviance and the residual deviance, which we'll talk about in just a second. And AIC, degrees of freedom, whatever. So once you have the model, we can do prediction from the model. One of the things that we need to be careful about is what we are predicting, and we'll go into this a little bit more detail later, but we can predict either the eta value, which is basically the linear term of what is just x beta, sort of equivalent to what y hat was, We can also sort of predict what is the expected value of the parameter. So in that case, that's sort of what I would call lambda hat. So in essence, that is x beta gone through the inverse link. And then I can also predict the response, which is the equivalent of predicting the y's. So I want to make sure that I'm on the right scale. So for right now, what I'm doing is predicting at the response level. So this is then going to be predicting counts. I am creating a new data set, so I'm calculating it, like I'm filling in the gaps, because again, these are each observed at years. It doesn't really make sense to predict there, but I just wanted a continuous line, smooth, put it in there. And so what we see is that we sort of fit the data, and we're sort of overshooting at the beginning, overshooting at the beginning, undershooting in the middle, and then overshooting at the end. But we get a sort of logistic curve growing, so it's at least mirroring the data in a sensible way as we go.
So why is the predicted value?
Yeah.
How do you differentiate between like the old y's and the predicted y's? The new y's?
Because they're not the same. Like, that's the old y, this is my predicted y.
Yeah, but if you're just calling them both y.
Like it's y pred, y predicted, something like that. I would indicate something that it's different as it comes out. And here, really, there's no difference between like the predicted y's, because I don't have a distribution, and the y hats, because like the prediction is just the average prediction here. So what I'm showing you here is actually sort of the lambdas. We'll get more into that when we talk about the Bayesian one on next Wednesday. Like again, which function we use to predict out and how do they look different. But so note that when I call the augment function with Broom, there's this argument type.predict that becomes important here to tell it which scale do I want to look at. And again, it's more obvious here that this is the case, but like again, in the case of like logistic regression, sometimes we want to predict the probabilities and sometimes we want the untransformed version of it. So that's what this is distinguishing between. So like whether it's the x beta eta result thing or gone through the inverse link to calculate the result from that. Yeah.
Are we using like all of data to fit the model at once? Like was that introduce some look-ahead bias in time series context?
So in the time series context, what we get is like there's an autocorrelational structure. So when we talk about like AR or MA models, it's basically that y at time t depends on y at t minus 1 in some sense, or other further lags out. And so we'll go through all of that. Here, we're not saying that in any way. So in terms of the data, it's all equally influential. No point privileges any other point, and it's not by virtue of like, we're not in some sense taking into account that this point knows that it's next to that point, other than just by incrementing x by 1, that affects the beta in some sense. Like, so we have that standard kind of regression type of interpretation of the intercept, like the slope of, for a unit change in x, y changes by this much. Now it's a little bit more complicated because it's not eta changes by that, which then goes through the link to get you a change in y. But there's nothing inherently used here about the sequencing of the data or the location of them being next to each other beyond sort of the typical way regression takes that into account. So we fit the model. We can sort of get a sense by looking here that stuff looks a little bit suspicious in that like I'm consistently overshooting, undershooting, overshooting. So that's indicative of a structure. And so again, the residual plot just makes that more obvious. And so we can think about saying, okay, like let's just look at the naive residual, which is just to say y is the observed value, and then my best guess for y is just the expected value of y given x from this model, which we've said in this particular case for a Poisson is lambda. And if we do that, this is what we see. So again, I've just drawn lines to show the residuals where they're above or below the 0 line. So what we do see here is, yeah, like at the beginning, my residuals are negative, then they're all positive, and then they're all negative again. That structure, that's the kind of thing we want to worry about. In terms of like our regression class, is there another pattern that you see here? Do we often complain about like when we're doing diagnostics for a basic regression? So basically what we call heteroscedasticity, the variance is not constant, it's getting bigger. What's the variance of a Poisson random variable, though? Lambda. So should we expect that? Like, the uncertainty should get bigger as lambda gets bigger, and that's in essence what we're seeing. And so the point is, very often with GLM models, the variance of the model is going to be constrained in some way based on the distribution that you chose. Same thing with binomial or Bernoulli. So in that case, the naive approach is probably not okay because we have a lot more uncertainty here. So maybe the residuals being big here is what we should just happen. Yeah.
But aren't we still? Yeah, the residual, the variance gets bigger on lambda as its mean increases. We know that on our.
Not lambda,
or on our
y gets, the
predicted
variance of
y.
y gets bigger.
But that shouldn't necessarily. Why would that mean that the residual aren't? I guess aren't the residuals still? We would hope IID. Or is that the whole purpose here? Is that with the Poisson regression, they're no longer? We're stating that they're probably no longer.
No, they're all IID, but they're all dependent on lambda.
Residual lambdas.
And what I've come up with my model is like my lambda is depending on x beta, and it's getting bigger. So the variance is getting bigger as we go. If it was the other way around, I'd expect a different pattern. Is there? Yeah.
Yeah, so in the traditional linear model, we usually have this assumption about the errors, that they're normally distributed,
Mhm.
like the epsilon and
Yeah.
is normally distributed. Is there a equivalent assumption when it comes to like the GLMs, like specifically here in the Poisson, like are we assuming something about how the error is behaving or not?
No, well, we are because we specified the model for the y's. I said the y's are IID Poisson,
Okay.
like conditional, like given the lambdas or given the x beta. So in that case, they're all Poisson, but then I'm stuck with the assumptions of the Poisson model, which is that the variance and the mean are both lambda.
Right. But then like the residual should follow a Poisson as well. Or not?
Not necessarily. I'd have to think about it more carefully. I'm not 100% sure, but like again, you could think about this and look for R sub I, like what is the distribution here? Like I think it should be a Poisson in some sense because like
Right, because y
this is a
really
constant,
Poisson and
like
the other
yeah,
one is constant.
it's like shifted or something. But the point is though that it's just the variability we expected to get bigger as we go. We're seeing the residuals get bigger as we go. What we cannot currently attribute is like, is that due to actual uncertainty or just assumption of the model as it goes through? So, yeah.
Sorry, just to clarify, the reason lambda is getting bigger is because x is.
Yeah, just from our model. Our model just says like as time goes up, the number of cases was increasing. So we are stuck with the fact that this is what's going to happen. This is a common problem with GLMs. We'll talk about it more like this is what's referred to as over or under dispersion. I have too much variance or too little variance because I'm constrained by the type of the assumption of the distribution I picked. And so there's ways of working around that. It's like quasi-Poisson models that allow you to fix it. We'll look at examples of that later on, but right now it's just to identify the fact that I can't use typical residuals here because of this. This is also, you're going to see structure in the residuals sometimes too because my observations are bounded at 0. I cannot get smaller values, so like there's certain things that I just cannot observe. There's regions that cannot possibly be a residual in this scope. You don't see that so much in Poisson cases. You'll very often see them in logistic regression cases where there's just regions of like emptiness because that's not possible given the constraints on the parameters. So that also makes things more complicated to look at. We're looking at a simpler case right now. So what I do want to resolve is this particular issue. So how do I address the fact that there's this additional uncertainty due to the variance of my model? How do I take that into account when I'm constructing the residuals so I get a better perspective of what is actual structure versus what is noise, potentially? Simplest approach for this, and it's like the trick that keeps on giving in statistics, is just standardize. So this is what's called a Pearson's residual. So basically what I'm going to do is I'm just going to take y, subtract its expected value, and then just divide by the standard deviation. Because I'm just going to then account for the uncertainty that's there that I can account for from the model. Whatever's left is fine. So you could think about this in like the Pearson's residual for the normal case are just basically a scaled version of the standard residuals. Nothing changes. You're just dividing by the same standard deviation, so it's just scaled constantly. No big deal there. In the case of a Poisson regression, I'm now just dividing by the square root of lambda. So accounting for that, so that basically those ones that where lambda is getting bigger get shrunk down to be smaller, so that everything is a little bit more of a fair comparison. And so this is what that looks like. So clearly the structure is still there, but note the right-hand side is not as big as it was before. It's more on the same scale. So it's basically saying, yeah, that's sort of what we would expect to see just by virtue of the fact that the uncertainty is getting bigger there. So once we take it into account, like this isn't the biggest problematic area. So we no longer have, like, here I'd argue we sort of have like one of these like fan-shaped heteroscedastic things. In reality, once we take into account the variability, not as big of a deal. It's more just the under and overestimation at the beginning and the end. Okay, so that's one option. Yeah.
It's a stupid question. I don't know. So, what if the residual, the volatility change over time, and you want to make a prediction, then you standardize based on this chunk of data, but of course it changes the next chunk of data.
Sure, but the idea here with the Pearson's residual doesn't care about that, because as long as I have some way of knowing what the variance is, because I've subset it on I, so like that's time in some sense, as long as I can estimate that in some reasonable way, I could move that along and like have a sliding window of some sense that will then account for that as I go. So you can, in practice, knowing what that is hard. It's not something like, I don't want to be like double dipping where I'm like estimating that from the data and then going back in. That's fraught, I will say. Here, we have a very simple model. We know it's wrong, but because it's a very simple model, we know exactly what that is. Makes it easy to correct for it. But it's just to say that more complicated, we may not have that option. There's an alternative, which comes from this idea of deviance, which is just a comparison between your model versus the best possible model, the optimal model. And so basically it's a measurement of the ratio of the likelihoods between those two things. So in this case, what we're going to define is the best model is basically the model where the expected value of that model is the observed value. So it's the oracle. You ask me, what's your best guess for yi? I'm just going to tell you yi back. I guessed exactly the right answer, what you had. So what we do is we basically just calculate the likelihood of the model. In that case, we calculate the likelihood of the model under your particular case, and then we work out that, and that's going to give us the deviance of the model. And so we generally write it like this. The 2 there is just to cancel the 2 that's often in the subscript of a bunch of things. It's the ratio of these two likelihoods, but if we rewrite it, or the log of the ratio of the likelihoods, we can just write it as the difference then between the log likelihoods. So it's sort of a simple term. And once we have that, we can then calculate the deviance for any given sort of GLM model. So what we'll go through is just derive these really quick for the normal case and then the Poisson model. So again, I'll post the notes with like a handwritten version of this as well. So the deviance is equal to 2 times the log likelihood of the best model the log likelihood of the model estimate like that. And again, the idea here being that under the best model, it's going to be let's just do it for so the normal model, our log likelihood of, so I'm just doing this for the mean. You'd normally have to take into account sigma squared. Let's just assume that's a known fixed value. So the sum of So that's the likelihood for a normal. So for the best, as I said, my expected value is just the right answer, the observed value. And then for the model, oh, I'm sorry. So whatever my guess is, my fitted value from it, so x beta. Okay, so deviance is equal to 2 times, then I've got, so this is the best one, 1/2 log 2 pi sigma squared minus 1 over 2 sigma squared yi minus yi squared. That's 0, it just goes away. Minus, then that cancels with that. My deviance is going to be, and then that negative cancels with that. That's similar, not quite, to basically think about it as the square of the Pearson's residual. Okay, for the Poisson case, the log likelihood
Professor,
yeah.
for the normal deviance there, it's 1 over sigma squared times the sum of the yi.
Yes, sorry, yeah,
Right?
there we go, yeah, thank you.
And it's y hats, or is there a single y hat here, or is it each yi has its own y hat that we're?
It's, yes, that's why I hat for whatever the prediction is for that particular y. Yeah, yeah. Sorry, so yeah, that should be a yi hat everywhere. For the Poisson case, I've got yi log lambda minus log yi factorial. And so here again, for the best, so deviance is 2 times sorry, that's yi log yi factorial. So here it's just grouping similar things. So those cancel. And then I'm going to just put this with that and that with that. So I'm going to get 2 times the sum of yi log. So what I've got is log yi minus y log lambda I. So that's just going to be the ratio of yi over lambda I hat. So that one does not have like an obvious analog to the Pearson's residual or anything else. but it's simple enough to sort of work through and calculate what it is. And so one of the homework questions will ask you to basically do this for like the binomial or the Bernoulli case to figure out what it is. So again, it comes from a weird place. It's not like obvious how it connects, but it's a straightforward kind of calculation to do to derive what is the deviance for one of these things. And given that it's like the ratio of these two things, it makes some sense. Like the closer your model is to the best model, the better, right? Yeah.
Is there any case where the best EYI given expectation of YI given X is not going to be YI itself? Or is
No,
that-
because that's just by definition. Like, again, I'm assuming the best possible model is one that just gives me my data back, like my observations back.
Does it connect with KL divergence? It looks like very similar.
It's been a long time since I thought about it in that context. Yes, it's basically, it amounts to like a likelihood ratio test in some sense, but it's a likelihood ratio test of the best model to your model. So yes, I'm sure KL divergence is in there everywhere, but that's just because KL divergence is everywhere. And it's been a long time since I took my grad theory class, put it that way. So the point is that the deviance in some sense can be interpreted like a sum of residuals squared as you go through. And so you can treat the individual observations then as basically being a residual. So this is just rewriting that result we just got, but now to put it back on the scale is like it's a sum of squared residuals, so I'm going to take the square root of it. The one thing that we do lose with the deviance is the sign of whether it's a positive or negative residual, which is an important thing to keep track of. So that's why we also stick that thing at the beginning. But in essence, this is what a deviance residual is for a Poisson regression model. And if you go back and you look at the summary output for one of these models, what we get is this residual deviance is that number calculated for this particular model. So basically calculating that likelihood from the data from what we got from our estimates of lambda to tell us what it is. And so again, the smaller that residual deviance is, the better, right? The closer to zero. Just like it's similarly like the residual, whatever it's reported for LM, like your sum of residuals squared, whatever that is, the smaller that is, the better your model is fitting in some sense. And so if we think about it in that way, we take the deviance that way, decompose it, calculate these individual residual contributions, go through and plot them, is we get something that looks very similar to what we were getting from the Pearson residuals. So in essence, by doing it in this way, by taking into account the likelihood in the model and all of that, we get something that is analogous, that in essence is accounting for that variability issue that we were just talking about. If we actually go ahead and compare naive residuals to Pearson residuals to the deviance residuals, they don't look that similar. They're on different scales. So that's one thing to keep in mind, that there is like apples to oranges at that level. But again, the main point of this is not so much the scale of them, it's the structure that's there. That's what counts more. And so once we do this and look at it this way, what we can see is that they're not the same, but the deviance of the Pearson residuals are giving us a very similar picture of what's going on. So I include the deviance residuals mostly just because there's a more deep theoretical underpinning to them. There's what's reported by R, they're what's reported by a bunch of these tools. Pearson's residuals are just easy. They're very simple to calculate. They're very intuitive to understand why they might work, but they're not sort of as justified across the board in terms of like a deep theoretical like connection to what you're doing. So they're both there, but in essence, for our purposes, a lot of the time, we just want to make sure that we are accounting for that variability in a sensible way. And then once we've done that, looking at the result to see structure, to see if there's something that we should do with the model or not. Okay? So that's the game that we're trying to play, or what we're trying to get to. So ultimately, deviance and Pearson are going to tell you the same story the vast majority of the time. I'm sure there are edge cases where they're slightly different, but I have not come across one in practice. Okay, so if we want to update the model, maybe we can account for this a little bit better, so add a little bit more flexibility. Again, not a good thing to do in practice, but a simple fix is just to add some polynomials, to add a little bit of like nonlinearity to it. So in this case, rather than using poly, I'm just directly adding a years squared term into the model. That allows some more flexibility. And so now what we can see is we're now getting an extra sort of bend in the curve, which does a much better job of accommodating this. So based on this, I might feel comfortable like forecasting maybe a year or two out. I would not feel comfortable like 5 or 10 years out. It's going to do weird stuff. So in that case, that's where you need to know the limitations of your model, limitations of the features that you've included. But this has at least given it enough flexibility to like fit the data substantially better than what we had before. So if I was trying to just do forecasting within this region, polynomials are not a bad option. Forecasting outside of the region, much less of a good idea. Again, we can then look at that quadratic fit and look at the results and see, okay, it's not enough data points to say definitively one way or another, but this looks a lot better. But note that it gives a much better picture of looking at the deviance of the Pearson residuals than it does looking at the naive or the standard residuals. This still looks like structure because it still has that fan shape. The variance is increasing, but again, as I said, that's expected in this particular model, so that's not a problem. Once we account for that, then we get a clearer picture and say, yeah, that looks okay. Okay, that's the classic frequentist approach. Again, we're not talking about how it's actually fit. It's using an iterative weighted least squares solution to like optimize that model to maximize the likelihood, to estimate those lambdas, or the betas in the model to then estimate the lambdas. So it works. It's still not an exact solution. So it's iterative. You may have problems of convergence. There may be numeric issues. We're not going to touch on those now. Bayesian model is basically exactly the same. We're, again, just leaning heavily on BRM to do it for us. So in essence, all that I've done is just swapped out the GLM function for the BRM function. Arguments are exactly the same, family Poisson, and it does the right thing. So goes through, fits it. We're fitting 4 chains, each with 1,000 iterations, so we get a 4,000 total draws. We get our estimates of the intercept in the year. So we didn't even look at these before. So minus 400 and positive 0.2. We go back. They're going to be very similar. So not exactly the same, but close enough. So once again, we're not seeing something dramatically different here. Again, we're also not messing with priors or anything else like that, so it's just picking the default option. So again, note flat priors for the intercept and the year, which is slightly different than what we got for the LM, because remember the LM had a prior on the intercept that was different. But again, this is one of these things that the person who wrote BRMS made choices. Most of them are sensible most of the time, but people might disagree. You can override them and change them if you want, again, beyond the scope of this class. And I'm sorry, no, there is an intercept term. Never mind, I don't know what I'm talking about. So the slope term for year is a flat prior. There's a student t prior for the intercept, but that's about it. Yeah?
Can you remind me what the difference between B and B year is?
This is just saying the default, and then this is just saying like the vectorized version of it. So you can basically just ignore that first line. It's not applying it to anything. It's just saying we are setting up this beta set of coefficients. The only thing that happens to be in there is year. So that's the only one that matters. So if we had extra coefficients, we'd include the quadratic term. That would show up as another line there. Look at the posteriors. Nothing looks weird about the distributions. The chains look like they mixed well. So again, nothing obvious, screamingly bad. All of that looks okay. Similarly, if we go back here, our hats are fine, close to 1. Effective sample size. So note, this model is harder to fit than an LM. So we're effective sample size, rather than like being around 3,000, 3,500 is now around 2,000. That's just the nature of the problem. It's harder to fit a GLM than it is to fit a linear model. So again, as long as those numbers are not in like the hundreds, like low hundreds, you're probably fine. And if they are too low, the simple solution is just to run it longer, increase the number of chains, or increase the number of iterations. Posterior predictive check. So this should tell us something about we're not doing a great job. So again, the black line is the kernel density estimate of our observed data. The light blue lines are our posterior draws of the y's. So again, the closer they are together, the better. But what this is basically saying is that like we are consistently overestimating the small values, underestimating the middle values, and then overestimating the big values, which is what we saw before. It's just telling us in a slightly different way. Is there a question?
I just didn't realize the lines were completely washed out by the
Oh,
projector.
yeah.
On the screen, they actually look
They are very, very
They're actually
faint.
visible and reasonably
Yes.
useful.
They're marginally
More
visible on the screen, but yeah, definitely not there. But it is telling the same story that we would see from the other fit, which is not surprising given the nature of the model. So it's there. Again, this is just a useful sort of sanity check that we're not like totally out to lunch and predicting something that doesn't make sense, because very often, particularly in the Bayesian case, if you have bad priors that are driving things, like overriding the data, that's where you would see this in this particular plot. In terms of the model fit, then, we can also then do these predictions with the intervals. So in this particular case, I'm doing the predicted draws, and then we are seeing the interval that comes from that for the y's. So again, this works in the same way as before. Predicted draws gives me the predicted distributions for the actual observed data. Do we notice something in that plot? Like, we haven't calculated yet, but does the empirical coverage look good?
Does it cover much of the points?
No, like the points are mostly outside of that. And so what we have here is basically our model's underdispersed. We have less variability than we need to accommodate everything. And that's being driven by our choice of model because of the Poisson, because the mean and the variance have to be equal to each other. That's driving this effect. So that's a model misspecification thing that we could potentially identify. So we'll go through and calculate those things and show them in just a second. But like just naively looking at this, once we show those distributions, we can see that there's a problem there. Residuals, so there is then similarly a residuals draw function. So what that is it's basically going to go through the process of like the predicted draws, calculate a y, but then it will then take the difference of that from the predicted value. So we can get residuals from this model so that we can then look at their distribution. So once we have those, I can then calculate something like this. So this is just showing the raw residuals without any kind of correction. Yeah.
Is the residuals draw function the same as doing the predicted draws or e-pred draw? And then just
I will have to double check.
calculate the
I'm pretty sure it's
residual
predicted draws minus y. Or no. I have to double check.
But it's
It'll be one of those two,
literally
yes.
that draw, and then so if you wanted the draws and the residuals, you could just do the draws and then say
Yes.
like
hmm
apply or apply. Or
Given what I'm saying, I'm almost positive that it's the predicted draws. So it's predicting y's, and then we're taking the difference from that.
And so it's just you could literally just do
You could do it yourself,
draws
yes.
and
This is just saving you a step of having that extra call to mutate.
But if you wanted both things, you
Yeah. But it lets us calculate those, and again, we get one residual per iteration, per chain, per parameter, and so we can then plot those. But note, BRMS, tidy Bayes, ggdist is dumb about that, and what it's going to give you is just the simple residual, the naive standard residual, which is not the right one. So if we do that, what you can see is the same pattern we're seeing before. The only difference is now instead of a point estimate for that residual, I've got a distribution of it, so we get some uncertainty around that. But note, it's getting bigger as we go, which is the problem we were just trying to address. So if we want to do a standardized residual, in this case, you need to tell it that. So you can pass in, I want a Pearson residual. It will do that calculation for you. And so now that looks a lot more like what we were seeing before. So the structure is still there, but now the uncertainty is sort of similarly consistent across the board. Yeah.
this is now the function in the SVM package now.
It is, but this is, I'm not changing the behavior of the standard residuals underscore draws function. That's there. My version, the only thing that it's doing is just including the chain and the iteration information in it. So this is a function that's part of...
Pearson type, the type equals Pearson argument exists in the regular.
Exactly. I'm not changing that behavior, yeah. So that comes from the package. With that said, it does not support deviance residuals. It's not that clever because it can't look at the model to like, it's not easy to infer then what is the appropriate deviance residual to do. So there's no option for that. So in this case, you're sort of stuck with Pearson. If you wanted to calculate the deviance residuals by hand yourself, you have all the pieces there. You could calculate them via mutate, but it's kind of a headache. This is nice, and as we showed, for the most part, the Pearson and the deviance residuals are going to be basically the same. So for expediency, we'll often just use this. If you really want the deviance residuals, you can calculate it yourself and go through. Any questions about that? So again, hopefully what we're seeing is this is exactly the same story we saw in the frequentist case. The only discrepancy is now that I just have a distribution on these things that I can carry through for whatever purpose. Model performance. So we can calculate these. The RMSE and the CRPS is not terribly useful in and of themselves. Those are like a model comparison criterion. So like once I have multiple competing models, I would then compare across these to see. At least the good thing is that they've sort of converged. They're consistent across these things, so they're fine. But they're not useful in and of themselves at this point. Only when I have competing models that I want to compare their predictive performance or their sort of precision accuracy trade-offs, then I could use that. But again, just to show that we can calculate them. And similarly, we can calculate the empirical coverage, and this just sort of quantifies what we were already just seeing, which is that the interval of this model is too narrow. But that is a property of the model because, again, we are constrained with what the variance can be based on our choice of a Poisson model. I believe I'll show you a brief example of how we might deal with this in the real world. Alternatively, just using a better model like the quadratic version of this accounts for a lot of that, then we don't need to worry about it. So the choices there are pick a different probabilistic distributional model to use, or pick a model with more features where that will then remove the need to deal with that particular problem. Either of them are acceptable, either of them can be useful, but they also have trade-offs. So again, the quadratic model fits the data better, but it's probably overfitting in some sense. So it's probably not going to be very good for forecasting versus the other model that is going to be like the underdispersed Poisson that allows me to increase the variability in a different way is going to be more flexible, but it's going to be a much more challenging model to fit, a more challenging model to understand what's going on. So that's the trade-off that I'm paying there, that it may do a better job of capturing the data, but in a way that I have a hard time explaining to my collaborators, potentially. So there's not a sort of universal, this is the one fix you'll use. We'll look at both examples, but the main thing is identifying that there is a problem and being aware that there's a problem and not just sort of sweeping it under the rug to say, okay, it's probably not the appropriate choice as is. So what we're going to give you is just a bunch of diagnostics and the million different ways things can fail, and that's to be expected. It's hard to do this in the real world. Once it fails, though, it's just important to understand why it failed and what's going on and what you might then do next, or at least how you can account for that failure and then describe it to the limitations of your result in some sense as you go on. So again, the famous Box quote, like, all models are wrong, some models are useful. This model is wrong and probably also not useful, but it is still at least catching the trend, so better than nothing, better than fitting a linear model. This comes up in poli-sci all the time where people start arguing that you don't need a logistic regression, you can just fit a linear model, because as long as you're not near 0 and 1, it's fine. It's not. Don't do that. It's wrong. But people will do different kinds of things, so this is definitely better than just trying to assume that this is not count data at all and just ignoring that. Taking into account the properties of the data is really, really important, even if that then introduces other problems that you have to solve. So,